Okay. Um, Hello and welcome to yet another lesson. We've been trying to cover the topics in the chemistry syllabus, and today we are going to be looking at atoms, molecules, and atomic structure. That's basically what we want to look at today. Um, okay. I still remain Anjorin Oluwafemi Excel. I will be your teacher for this topic. I hold a BSc in chemistry from the University of Ibadan. I also have a PGD in science education from Federal College of Education Technical Akoka, and also I have a MSc, a master's degree in environmental and in analytical chemistry from the Redeemers University. So I'm going to be taking you on the journey of atoms, molecule, atomic structure. Let's start off by looking at the lesson objective for this topic. Okay. So by the end of this lesson, it is expected that you should be able to distinguish between atoms, molecules, and ions, identify the contributions of scientists to the development of atomic structure, deduce the number of protons, neutrons, and electrons from atomic and mass numbers of an atom, apply the rules guiding the arrangement of electrons in an atom, identify common elements, exhibiting isotopy, relate isotopy to mass number, and perform simple calculations relating to isotopy. It's also expected that by the end of this lesson, I should be able to differentiate between the shapes of orbitals and determine the number of electrons in sp atomic orbital. Also to identify layout and structure of the periodic table, recognize and classify elements into major families, the alkali metals, halogens, noble gases, and transition metals, and so on and so forth. Also, you should be able to describe how ionization energy, ionic radius, electron affinity, and electronegativity vary across periods and down groups. So these are basic things or basic knowledge you should be able to, or basic things that you should be able to do by the end of this lesson. All right, our first slide lays the foundation. And with this first slide, I try to define what an atom is. I said an atom is the smallest unit of matter that retains the identity of an element, and it consists of three fundamental particles. So when you're talking about the smallest unit of matter that retains the identity of an element, we are referring to an atom. And it is made up of three sub-particles. We call them subatomic particles. And these particles are protons, which are positively charged, neutrons, are neutral, they don't carry any charge, and then electrons that are negatively charged. So the protons and neutrons are located in the nucleus, as you can see from the diagram or the picture that's on the right hand side of the screen. So the neutron, the protons are localized at the middle of the atom in a place called the nucleus. Why the electrons are found in the number of protons in an atom defines the atomic number, and the sum of protons and neutrons defines the mass number. So you can see the subatomic particles are basically protons, neutrons, and then electrons, as you can see from the screen there. Okay, so the next thing that we need to look at is the concept of atoms, molecules, and ions. Now, let's look at molecules first. A molecule is a group of two or more atoms that are chemically bonded together. There are two or more atoms, they are chemically bonded together. Now, molecules can be formed from atoms of the same element. Example, oxygen. The oxygen molecule is made up of two atoms of oxygen, or from different elements. Example, H2O, water. Molecules may be classified as either covalent, where electrons are shared, or ionic, where electrons are transferred. We're going to look at this as we go along in this lesson. The next thing that we need to also establish or to also define is an ion. An ion is an atom or molecule that has gained or lost one or more electrons, resulting in a net electrical charge. So ions are categorized as one, either to be cations, or you can also have the other one that we call the anions. The cations are positively charged ions. Example, sodium ion, magnesium ion. Those are positively charged ions. They're called cations. While the negatively charged ions are called anions. An example, chloride ion, sulfate ion, and so on and so forth. Now, the gain or loss of electron occur to achieve a more stable electronic configuration, often resembling that of noble gas. So what happens most of the time with this loss or the gain of electron is that most of the time, these atoms are trying to, achieve the noble gas, state because it's more stable. So you see them either losing or taking on. I'll give you an example. Sodium will be very, very willing to give off its own electron, that extra one electron that, ion that it has rather. And when it does that, it attains a 2-8 system. That is, it has 2 and then 8 electrons in the outermost shell, which is the valence shell. 8 is an octet state and it is more stable. So, and if you look at the reverse, is chlorine. Chlorine is more than willing to always accept an electron. Why? Because chlorine has 7 electrons in its outermost shell. So it needs 1 electron to be able to, get to the octet state or to be able to have a noble gas, valence shell, so to speak, that is having a total of 8 electrons or 8 electrons in its outermost shell. So chlorine is more than willing to take on 1, and that is what happens. So the gain or loss of electron occurs to achieve a more stable electronic configuration, often resembling that of noble gases. Okay, all right, that's good. So the next thing that we need to look at is historical development of the atomic theory, historical development of the atomic theory. And there are so many people that have contributed to the atomic theory, and I will just try to just use a table to look at their contributions and the name of the sciences. So the first science is Dalton. He proposed that atoms are indivisible particles. Atoms of the same element are identical. These are some of these propositions, towards atomic theory. Another scientist is J.J. Thomson that discovered the electron using the cathode ray to propose, and he proposed the Plum-Paulding model. So that's for J.J. Thomson. Also for Rutherford, we have Sir Rutherford proposed the nuclear model of the atom through the gold foil experiments, scattering experiments. That was one of the things that Rutherford did. Then we have Harry Millikan measure the charge of electron using the oil drop experiment, and then mostly determine that atomic numbers define the identity of an element, reorganize the periodic table by atomic number. It was mostly the did that for. Then we have Neil Bohr, a German scientist that proposed that electrons move in discrete energy levels, shells around the nucleus, and that was the proposition from Neil Bohr towards the atomic theory. So these are various scientists that have worked. I would like to just give this as an assignment to you that you should try to read up, in detail about the works of the scientists and how they came about some of those things that they discovered and proposed. It will help a great deal. All right, so let's move along now and look at the next one. I want to look at the atomic structure, electronic configuration. Pardon me, that's a typo. Electronic configuration, atomic number, mass number, and isotope. So these the first thing that we need to define is what is an atomic number. Atomic number is denoted by the letter Z, and the atomic number represents the number of protons in an atom's nucleus. It represents the number of protons in an atom's nucleus. That's the atomic number. Now, the atomic number is unique to each element and determines the identity of the element. It is the identity of the element. So the peculiarity of an element can actually be drawn out or can be derived from the atomic number of that particular element. For instance, hydrogen has an atomic number of one proton, while oxygen has an atomic number of 8. It has 8 protons, so the atomic number differs based also on the position on the periodic table. Now, mass number is denoted by the letter A. The mass number is the total number of protons and neutrons in an atom's nucleus. The total, that's the combination of the protons and neutrons in an atom's nucleus, is referred to as the mass number. Now, since electrons have a negligible mass, they do not significantly contribute to the mass number. Now, let's look at this particular example to drive home the point. Now, an atom has an atomic number of 17 and mass number of 35. What is the number of protons, electrons, and neutrons of the atom? Now, don't forget, from our definition, we established that atomic number is synonymous to the number of protons in an atom's nucleus. Now, what does that connote? It means that the number of protons is equal to 17, which is the number of the atomic number that we are given. Also, the number of electrons is 17. Now, if it is neutral, and basically the assumption is that the atom is electrically neutral. So if it's electrically neutral, it means that the number of protons will be the same as the number of electrons, so that there will be a balancing, so to speak, positive, negative balance, so to speak. Now, the number of neutrons on the other hand, we need to calculate that out. But don't forget that from our definition of mass number, we said that the total number of protons and neutrons in an atom's nucleus is what we refer to as the mass number. Now we're given the mass number to be 35, and we've also been able to establish that the number of protons is 17 from the atomic number. So the number of neutrons is simply what's taking away 17 from 35, and that will give us what? 18, and simple and straightforward. So you can lay your hands on different, atoms and look at their mass number, and then try to work out, look at their mass number, atomic number, and try to work out the number of protons, the number of electrons, and number of neutrons, and you discover that it is pretty straightforward, and you will actually get it. All right, so let's move along now and talk about the electronic configuration. Now, the electronic configuration of an atom is the representation of the arrangement of electrons distributed among the orbitals, shells, and subshells. Now, commonly, the electronic configuration is used to describe the orbitals of an atom in its ground state. But it can also be used to represent an atom that has ionized into a cation or anion by compensating with the loss and gain of electron in their subsequent orbitals. So the basic thing is that when we talk about the electronic configuration, we use it to represent the arrangement of electrons distributed among the orbitals or among the shells or subshells, and we have different orbitals. We also have different shells, as the case may be, So that's what the electronic configuration is. So as we go further, you'll be looking at different orbitals and how electrons are filled into it, and what amount of electrons can be contained in each orbitals and all that. So we're going to be looking at that, very, very shortly. So that's very important. Now, the valence electrons in the outermost shell are the determining factor for the unique chemistry of the element. Now, the valence electron, the number of valence electrons will determine the group the element will belong to. It will determine the reactivity of the element and all that like that. So the electronic configuration is very important, and it's important that for us as chemistry students, that we understand this and we are able to, write out the electronic configuration of different elements as we come across them. Okay, so the electronic configuration of elements, still continuing that now. Now, I've decided to list out for you the 11 electronic configuration of elements as seen on the periodic table. Now, mind you, what I have done is to drop this electronic configuration into orbital shells. I'm going to talk about this very, very soon. Just hold on. And what I mean is into orbital shells like the s orbitals, the p orbitals, and so on and so forth like that. Now, we can also write electron configuration without putting them into orbital shells. I will give example as I run down this 11 electronic configuration that I've stated out now. Now, lithium 1s raised to power 1 or 1s1, so to speak. Why? Because, sorry, hydrogen, pardon me. Hydrogen has just one, is number 1 on the periodic table. Helium is number 2, lithium like that, it goes on like that. Now, when you get to sodium, we have its position 11 on the periodic table. Now, the atomic number is 11. So how do we now write the electronic configuration? What we do is that we say 1s2, 2s2, 2p6, and 3s2, s1. I'll tell you how this is done very, very shortly, just hold on a minute. Now, we can also write sodium to be just what? 281. Just going by the shells now, which is the KLM shell, you understand? So you can have 2 in the K shell, you can have about 8 in the L shell, KL, then you can have M shell having about 1, 1, so to speak, So it can either be in orbital shells or in orbitals or in shells like the KLM shell and the likes like that, And for us to be able to know the number of electrons that will fill each of the shell, is for us to use a simple formula that says 2n squared. N represents the number of the shell. Like take, for instance, if you have the K shell, that's the first shell. K is the first shell. So what you have is 2 times 1 squared. So it will tell you the total number of electrons that can be, resident, that you can put into the K shell. And if you do that, you say 2 times 1 squared. Anything 1 squared is still 1. So it's 2 times 1, which is 2. So the total number of electrons that you can put into the K shell is 2. The L shell, on the other hand, that's the second shell. So you do a 2 multiplied by n squared. N in this case is 2 because L is the second shell. So you have what? 2 times 2 squared. 2 squared is 4. So it'll be 2 times 4. That's 8. So the maximum number of electrons that you can put into the L shell is 8 electrons. So you can work out the rest for me. M, N, O, and you run it down like that, following the 2n square rule. Okay. I hope you get that concept. Make sure you work it out. Work it out. Put your comments in the your answer in the comment section, and then I'll react to it appropriately. So as a class activity, I want you also to write the electronic configuration of for element 12 to 20. So also do that. You can also put it in the comment section. I will run through them. I will look through them closely. And if it's correct, I'll give you a thumbs up, Okay, so please try it. Make sure that you engage it. It's very important. Don't stay idle. Engage. Thank you so very much. All right. Now, let's move along now, and let's go to the next one. The rules for assigning electron orbitals. There are certain rules for that we must follow and that we must take note of if you're going to assign electrons into different orbitals. And that was what I was talking about the other time. Now, the first rule that is very important is the Pauli exclusion principle. The Pauli's exclusion principle. Now, it states that no 2 electrons can have the same 4 quantum numbers. No 2 electrons can have the same 4 quantum numbers. And what are the quantum numbers? We have the principal, the magnetic, the azimuthal quantum number, the spin quantum number, which is the N, L, M, S, and the likes like that. So the first 3, N, L, M, may be the same, but the 4th quantum number must be different. A single orbital can hold a maximum of 2 electrons, which must have opposing spin. So even if you have the principal, the magnetic, and the azimuthal quantum number as the same, but you discover that the spin will not be the same. The spin can either go the positive way or the negative way, as the case may be, So the spin will always differ. One may spin up, the other may spin down. And that's one thing. So you may have a plus half and a negative half, as the case may be. That is for the Pauli's exclusion principle. And now, this tells us that each subshell has double the electrons per orbital. The s orbital has 1 orbital that can hold up to 2 electrons. The p subshell has 3 orbitals that can hold up to what? To 6 electrons, because the p orbital is degenerated into 3. We have the px the py, and then the pz, you understand? And each of the px, py, and pz can hold what? A maximum of two electrons spinning down, spinning up, as the case may be. So it can hold a total of 6 electrons. Now the d subshell has 5 orbitals that can hold what? 10 electrons. And then the s subshell has 7 orbitals that can hold what? A total of 14 electrons. So these are very, very important that we take note of that. Okay, I haven't talked about Pauli's exclusion principle. Let's look at this. Okay, let's look at this example just to buttress what Pauli's exclusion principle is talking about. Now, the first 3 quantum number of an electrons are N1, L equals to 0, and M equals to 0. Only 2 electrons can correspond to this, which would be either Mx, that's the spin quantum number, being negative half or plus half. As we already know from our studies of quantum numbers and electron orbitals, we can conclude that these 4 quantum numbers refer to the 1s subshell. If only one of the ms value are given, then we should have 1s1 denoting hydrogen. If both are given, we'll have 1s2 denoting what? Helium. Visually, this can be represented as this, For hydrogen, you just have 1, and that is just 1 spin going up like that. For helium, you have 2, 2 atomic number. So it has 1 spinning up and the other one spinning down. So as shown, the 1s subshell can hold only 2 electrons. And when filled, the electrons have opposite spin. And that is what you can see with the helium atom. You have one spinning up, the other one spinning down, as the case may be. Okay. All right. So that's an example to buttress that. Now, rules for assigning electron orbitals continuation. We look at Hund's rule now, or Hund's rule. When assigning electron in orbitals, each electron will first fill the orbitals with similar energy. The electrons will fill the orbitals with what? With similar energy, also referred to as the generate. Now, so what we're talking about is that a 1s orbital will be filled first before you go and fill the 2s orbital. A 2p orbital will be filled first before you fill the 3p orbital, and that is how it is, you understand? So you cannot just jump from 1s and go and fill, a 3p or a 2p, as the case may be. So it must fill the orbital with similar energy. It must have similar energy before pairing with another electron in a half-filled orbital. Now, atoms at ground state tend to have as many unpaired electrons as possible. When visualizing these processes, think about how electrons are exhibiting the same behavior as the same poles on a magnet would if they come into contact. As negatively charged electron field orbitals, they first try to get as far as possible from each other before having to pair up. And that is how it's, that is how it is. You can visualize it that way, you understand? And that's that if you look at the electronic configuration of the nitrogen, where the atomic number is 7. Now, when you look at it closely, you discover that it is written as 1s2, 2s2, and then the 2p3. That's the electronic configuration. 1s2, 2s2, 2p3. That's a total of 7 there. Now, look at the way Hund says that it's going to be filled. First, what happens is that you see them filling up from the lowest energy, the orbital with the lowest energy, and then it graduates up like that. Now, something interesting is this. You know that the s orbital can contain a maximum of 2 electrons. So you have what? One spinning up, one spinning down for the 1s. That satisfies the 1s orbital. We move to the next orbital, which is the 2s. You have one spinning up, one spinning down. It satisfies the 2s orbital. Now, get to the p orbital. Don't forget that the p orbital can have a total of 6 electrons that it can carry. But what we have left is just 3. it will now be very, very wrong on our part to start by saying that, okay, let me put the px, let me just fill 2 into the ps and just have one spinning up, one spinning down. It is wrong. But what do? We first spread it across all the degenerates, So we have 1, 1, 1 in the p orbital. And that is how we write. So we cannot just spread it up like that, but we just split it over. And we have that. We can clearly see that the p orbital are half filled, as there are 3 electrons and 3 p orbitals. This is because Hund's rule states that the 3 electrons in the 2p subshell will fill all the empty orbitals first before filling orbitals with electrons in them. If you look at the elements after nitrogen in the same period, that is oxygen, with an atomic mass of 8. Now, its electron configuration is what? 1s2, 2s2, and then 2p4. Now, let's look at it together. Now, you can see that after the 2s orbital had been satisfied, it has gotten its 2 electrons, maximum 2 electrons. Now, when we got to the 2p orbitals, what did we do first? Initially, we filled everything up, but then we were left with 1. And then what happened? You can now bring it into the px orbital. That's the 2px orbital. And then you have one, spinning up and the other one spinning down. But the 2px and the 2py rather, and the 2pz will still have just one electron in them. So oxygen has 1 more electron than nitrogen. And as the orbitals are all half filled, the electrons must pair up. And that's one thing about that. I hope you get the concept. Okay, just let me have your feedback in the comment section so that I will know that you are actually flowing with the topic. All right. Now, rules for assigning electron orbitals. We've want to talk about the third rule now. It's called the Hofbau's principle, and it states that in building an atom, electrons are filled into orbitals in order of increasing energy. So electron-filled orbitals in a way to minimize the energy of the atom. Therefore, the electrons in an atom fill the principal energy levels in order of increasing energy. Now, the electrons are getting further from the nucleus. The relative energy of the orbital is shown. Now, the order of level field is then you have the 1s orbital being filled first. Then after that, the 2s, then the 2p, then the 3s, then the 3p, then the 4s, then the 3d, then the 4p, then the 5x. And you can see that, with this diagram on that we have by the side here. So that is how it has been filled. So you just move from the lowest energy and then you ascend like that upward. And that is how orbitals are filled how electrons are filled into the different orbitals that we have. Now, note the energies of the D and F level vary with their occupancy. So we should take note of this. Okay, having said that, let's quickly dive into we have established what isotopy is earlier. We've said to try to combine isotopy and mass number together now. Okay, so isotopes are atoms of the same element that have the same number of protons but different number of neutrons, leading to different mass numbers. I'll take that again. Isotopes are atoms of the same elements that have the same number of protons but different numbers of neutrons, leading to different mass. Example, this particular example here. Now, carbon has 2 stable isotopes. We have carbon-12 and then carbon-14. Carbon-14 is very, very important for radiological work, but maybe we'll talk about that some of the time, probably when we're looking at nuclear chemistry. Now, so carbon has 2 stable isotopes, so carbon-12 and then carbon-14. And now both isotopes have 6 protons, but carbon-12 has 6 neutrons. Why carbon-14 has 8 neutrons? You see what is happening there? They have different mass number. But one thing you see with them is that they have the same number of protons, but different number of neutrons. Therefore, they will have a different mass number. Carbon 12 has a different mass number compared to what carbon 14. And also their neutron number is different, but there's a convergence when it comes to their proton. Their proton numbers are the same. Example 2. Let's now use this to do a little calculation now. A sample of element X contains 75% of 35X and 25% of 37X. These are isotopes of a particular atom. And when you look at it close, you can know that we're talking about chlorine here. Now, it said calculate its relative atomic mass. How do we do that? We bring the percentage and we multiply it by the what? The mass number. And then we add it together. We add them together. So you bring the percentage of one, you multiply by the mass number. You multiply. You bring the percentage of the other. You add it to the. You multiply by the mass number. So when you do that, you get that a very simple, straightforward calculation. Percentage multiplied by the mass number plus, that's for elements A, X, elements A. Let me just call them A and B now. And then isotope A, and then percentage multiplied by the mass number for isotope B. So when you add them together, you get the relative atomic mass. So you can actually use that to calculate the relative atomic mass. And when you do that, you have 35.5, which is the relative atomic mass of the element called chlorine. Okay, all right. See, I hope this is you understand this. Please put it in the comment section so I know that you are actually getting the concepts. Thank you very much. All right. So let's move along now and talk about the shapes of S and P orbitals. So we're talking about S orbitals, P orbitals, D orbital, F orbitals, and so on and so forth before. So I want to look at specifically the shape of S and P orbitals. The shape of atomic orbitals, is crucial in understanding the distribution of electrons in an atom. Orbitals are defined by quantum numbers and describe the probability of distribution of finding an electron in a particular region around the nucleus. So we can have the s orbitals. The s orbitals in shape, they are spherical. They're spherical in shape, meaning the electron density is evenly distributed around the nucleus. Each energy level starting from n equals to 1 has one s orbital. Okay. Now, what is the capacity? The electron capacity of the s orbital holds a maximum of 2 electrons. It can't take more than 2 electrons. I've talked about this before, so just reiterating it, for emphasis sake. The p orbitals, it has a dumbbell shape, with a region of high electron density on either side of the nucleus. So each energy level starting from n equals to has 3 p orbitals, which is designated as px, py, pz, and it's oriented along the 3 axes x, y, z. Electron capacity, each p orbital can hold a maximum of 2 electrons. So 3 p orbitals can hold a total of 6 electrons. I've also talked about this before. Okay, all right. So now let's move along now and talk about periodic table and periodicity of elements. Now, the periodic table organizes elements according to increasing atomic number, and it reviews the periodic pattern in the properties of elements. Now, the periodicity of elements is reflected in the repeated trends in properties like atomic size, ionization energy. Sorry, please. If you look at the diagram at the right-hand side of my screen, one of the things that you see with the diagram is that you see different elements, arranged, and then you can see different families also. And if you look at the first one there, we call them the group 1 element or the alkali metal. The group 1 element or alkali metals consist of lithium, sodium, potassium, rubidium, cesium, and francium. So these are the group 1 or the alkali metals. That's the first group in the periodic table. And the characteristics of the alkali metals are they're highly reactive, especially with water. They have a single electron in their outermost shell, which they readily lose to form cations. So example is sodium and every other ones, the potassium, they want to lose that extra electron, and then when they do that, they form cations. So that's the first family. The second family is the alkaline earth metal, which is the group 2. Please pardon me, that's a typo. It's group 2, not group 1. Please, I'm very, very sorry. Very sorry. So this is alkaline earth metals. That's the group 2, group 2 on the periodic table, as you can see. And it consists of beryllium, magnesium, calcium, strontium, barium, and then radium. So those are the group 2 elements. They have 2 electrons in their outermost shell and are the second most reactive after alkali metals. They are a strong reducing agent, meaning they can donate electrons quickly. They are also good conductors of heat and electricity. Physically, they have low density, melting points, and then boiling points. That's for the group 2 elements. We have the group 3 to 12 elements. It's just in between, the periodic table. So to speak, at the center of the periodic table, we have this group that we call the transition metals. Just somewhere here, you see it here. You have these and up to like that. So they are group 3 to 12. So you have the scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc, and it goes on like that. So that's the group 3 to 12 in the periodic table. Now, and they are also referred to as the transition metals. They are very, very important too. The transition metal lie from group 3 to group 12. They have more than one oxidation state, meaning they can have many oxidation numbers. They have low ionization energy and high conductivity. Aside, they have high melting and wonderful uses, so many other wonderful uses of the what's it called, the transition metals. I would advise that you should go online and also search and study more about them, and you'll be glad you did. Okay, all right. So let's move along now and talk about the post-transition metals. That is the element that occurs after the transition metals. And if you look at it closely, the elements are, from group this 13, 14, 15, 16, 17, 18, like that, those are the post-transition metals, so the post-transition metals are located in between the transition metals and the metalloids. They span from group 13 to 16. They have some characteristics of transition metals, but are soft and conduct more poorly than transition metals. Their melting points are lower than transition metals. We also have the metalloids on the periodic table. The metalloids display properties in between metals and non-metals. They're just in between metals and non-metals. Now, only 6 such elements exist, of which 3, that is boron, silicon, and germanium, are semiconductors, and they find valuable uses in the electronic world. The lie between group 13 and 16. Metalloids are not as good conductors of electricity as metals, nor are they as ductile as metals. They are brittle and can break easily. So that is that for metalloids. So we also have the non-metals on the periodic table. So the non-metals are on the top right of the metalloids, spanning group 13 and 16. They have high electronegativity and ionization energy and are poor conductors of heat and electricity. They exist as gases like oxygen or solids like carbon. Although it is in group 1, hydrogen is also considered as a non-metal. So the next one that we have is the halogen family. Very important, extremely reactive family, I must say. The halogen family lie in group 17. They are highly electronegative and reactive, requiring one electron to complete their outermost shell. Hence, they typically exhibit a -1 oxidation state. And they form salt with metals. They form salt with metals. So that's the halogen family. Then we have this family that does not want any interaction whatsoever. It just wants to stay on its own. It is called the noble gases. You know, the elements in the group 18 are called noble gases. They have complete outermost shells, resulting in stable electron configuration. Hence, they are the least reactive group on the periodic table, giving them nomenclature in and boiling point are colorless and odorless. That's the noble gases. We also have other groups like the lanthanides and then the actinides on the periodic table. You can go and look at them closely on your own, and you will get so much from studying that. Okay, although it's beyond what you should look at in your syllabus, your JAM syllabus, but you can just check it out for knowledge sake, you know. All right. So the periodic trends now, there are different trends that occurs on the periodic table. Basically, the ionization energy, their unique radii, and so on and so forth. How do they trend on the periodic table? First and foremost, the ionization energy is the energy required to remove an electron from an atom in the gas phase. That's ionization energy. Now, across a period, ionization energy increases because the nuclear charge increases, attracting electron more strongly, making it harder to remove electrons. Now, down a group, ionization energy decreases because the outermost electrons are further from the nucleus, and the shielding effects of inner electrons reduces the nuclear attraction. So that's that for the trend of ionization energy. Increases across the period, decreases down the group. Ionic radii refers to the size of an ion. Across the period, ionic radii decreases as the nuclear charge increases, pulling electron closer to the nucleus. Down a group, ionic radii increases because the additional electron shells are added, increasing the distance from the nucleus. So what is the trend of ionic radii on the periodic table? Across the group, it what? It decreases. Down the group, it does what? It increases. Okay, all right. So we look at electronegativity too. We say electronegativity is the tendency of an atom to attract electron in a chemical bond. Across a period, electronegativity increases because the atom has more protons and a greater pull on the electrons. Down a group, electronegativity decreases because the atoms are larger and the outer electrons are further from the nucleus. Now, electron affinity is another one. Electron affinity is the energy change when an electron is added to an atom in the gas phase. That is what electron affinity is. Now, across the period, electron affinity becomes more negative. That is, energy is released as element approaches a stable octet configuration. Now, down a group, electron affinity becomes less negative because due to increased atomic size and electron shielding. Okay. All right. Having said that, we'll look at chemical bonding and what does chemical bonding refer to. We'll look at this. We'll also look at the metallic bonding, and so on and so forth. So let's quickly run through chemical bonding now. Please, if you have any question, I beg of you, if you have any question, please put them in the comment section. But rather, what I will do is that let me take a breather at this point, and I will continue from chemical bonding in the next lesson. I don't want to just do a stretch like that. I want you to be able to take in those things I've given, digest them, understand them. Then we'll run with chemical bonding when we continue this video again. So thank you very much. I will also do the what's it called? I'll do the evaluation of the lesson when I continue with chemical bonding. So I will take a pause here, and then I'll continue with chemical bonding, and then I will do a summary and then evaluate the class as I'm supposed to thereafter. So that will be all for now. I'm going to stop here. And then after that, we are going to have the chemical bonding, and also I'm going to do an evaluation and do a summarization or a summary rather of the whole topic. Thank you, because we still have atoms, it's like a part one, part two. So I don't want to rush over the whole thing. Let's take it bit by bit for us to be able to assimilate properly. So if you have any question, there's an area that you are confused about, just send it to the comment section. I will look through it and then I will respond accordingly. Thank you very much for listening. I'll see you in the next class.